Today I'll be talking about the introduction of standard model of particle physics. We will see about the different types of fundamental particles, their properties and their antimatter properties. Raguveer will talk about the Large Hadron Collider. Okay, let me start. From the Victorian era, physicists thought the most indivisible particle was the atom. The stuff periodical table was made of. But later it was found that atom was made of even smaller particles, electrons and nucleon. Nucleons are the particles in neutrons, which are proton and neutron. Only in the last few decades, we found that neutron and proton are made up of even smaller particles, the fundamental particles. The electron was also the smallest particle. They belong to a group of fundamental particles known as leptons. Uh, since 1950s, only during from the 1950s, the theories and experiments of many particle physicists led to the foundation for the high energy physics. Everything in the universe is made up of fundamental particles, governed by four fundamental forces. Our best understanding of this is the Standard Model. To put the Standard Model in just two lines, we can say that it is the explanation of how the building blocks interact and how it is governed by four forces. It's just two lines. It's simple, but the math involved is very, very complicated. Okay. All matter around us is made of elementary particles, true building blocks of matter. These particles occur in two distinct types, quarks and leptons. You can see quarks in purple and leptons are in green. Each group consists of six particles which are related in pairs or generation. The lightest and most stable particles make up the first generation, whereas the heavier and less stable particles belong to the second and third generation. Up and down are the most stable, and every matter in the universe is made up of up and down quarks, and top and bottom are like the heaviest and thus very, very unstable, and when they will decay into up and down quarks. Eventually they will decay into all stable particles in the universe belongs to the first generation. Any heavier particles will quickly decay to more stable ones. The six quarks are paired in three generations. The up and down quark for first generation, charm and strange, the second generation, the top and bottom are the third generation. The quarks also come in three different colors. Yeah, I said colors. Red, green and blue. They only mix in such a way to form colorless substance. These are not actual colors actually, because quarks are too small. It is not actual colors. It is but an analogy to understand the quantum chromodynamics, which we will talk about in the coming lectures. It is an analogy. Proton has two up quarks and one down quarks. In that, there are three quarks, right? One has to be red, and other has to be green, and the other has to be blue. Only then they can combine, they can interact, and they can form a proton. They have to be red and green and blue will be colorless, right? So any combination has to lead to a colorless substance. The six leptons, the green things, are arranged in three generations also. The electron and electron neutrino, and muon and muon neutrino, and the tau and tau neutrino. The electron, muon and tau all have an electric charge. You can see the charge in the in each cell. The second number is the charge. You can see the charge, all of them is -1, and they also have masses. Electron, muon and tau has masses, but the neutrino counterparts little to no mass. It has very, very, very low mass. In each cell, the top number is the mass of the substance. You can see that neutrino has the very least mass, and that's why it can't decay. It can't decay into any lesser elements. That's why it is stable. Neutrinos are very stable. Each and every second, millions of neutrinos are passing through this. Okay, let me talk about force carriers. There are four fundamental forces at work in the universe. the strong force, the weak force, the electromagnetic force, and the gravitational force. They work over different ranges and have different strength. Gravity is the weakest, but it has an infinite range. The electromagnetic force also has infinite range, but it is many times stronger than gravity. The weak and strong forces are effective only over a short range and dominate only at level of subatomic particles. Despite its name, the weak force is much stronger than gravity, but is indeed the weakest of other three. The strong force, as the name suggests, is the strongest of all four fundamental interactions. Three of the fundamental particles result from the exchange of force carrier particles which belong to a broader group called bosons. Bosons are here, it is in red colors, you can see. Force carriers, force particles. It is just a ripple or just excitation in the field. Every particle has its own field. The ripples and the excitation in the fields are of the particles. It's simple. Particles of matter, every quarks transfer discrete amount of energy by exchanging bosons with each other. If there is, let's say, take example of proton. There are two up quarks and one down quark, right? In between the quarks, two up quarks, there is an exchange of particle through which it holds together. It's simple. Each fundamental force has its own corresponding boson. The strong force is carried by gluon, the electromagnetic force is carried by photon, and W and Z bosons are the responsible for weak force. Although not yet formed, graviton should be the corresponding force carrying particle of the gravity. Till now, we didn't find gravity. We we can't find gravity up to the technology still needs to advance, because in the Large Hadron Collider, where we found any colliders, accelerators, we found these fundamental particles, which all the particles are high energy, but gravity is 10 to the power 40 times weaker than strong force. It is very, very weak. We can't find graviton because it is very less. It has very less energy, but we will find it. We will eventually find it. The standard model includes the electromagnetic strong and weak forces and all the carrier particles, and explains how these forces act on all of particles. However, the most familiar force in our everyday lives, gravity, is not part of the standard fundamental model, as fitting gravity comfortably into the framework has proved to be a difficult challenge. We know that quantum theory used to describe the micro world, and the general theory of relativity used to describe the macro world. And these two are difficult, like very, very difficult to fit into a single framework. No one has ever managed to make the two mathematically compatible in the context of standard model. But luckily for particle physics, when it comes to minuscule scale of particles, the effect of gravity is so weak as to be negligible. We can see the mass here, right? Just compare. The mass is very low. It has little to no interaction with gravity. That's how all the experiments in the Large Hadron Collider is possible without any effect from the gravity. Only when the matter is bulk at the scale of human body or planets only, for example, does the effect of gravity dominate. Like gravity dominates only in like macro region. It doesn't have a particular like meaning or effect in the micro region. So the standard model still works well despite its reluctant exclusion of one of the most fundamental forces. And now let's talk about this. We know that molecules are made of atoms and atoms are made up of nucleus and leptons, and let's see the important matter here. All of the matter in the universe accounts for only 5% of it. Dark energy and dark matter constitutes most of our universe. But dark energy and dark matter is not like explained in the standard model of particle physics. We will cover that in the coming lectures. Quarks. There are up, down, charge, strange, and top, bottom. You can see that every particle has a charge and spin. It charge does not accounts to like -1 means -1 charge of electron. It doesn't count like my 1/2 means 1/2 of charge of electron. It doesn't count like that. It is an you need to come out of the standard physics that you have learned, and these type of charges are known as lepton charges. They have their own values. um, okay, I will carry on with the next one. Mesons. Meson is an anti-particle and antiparticle. Why? But we all know they annihilate each other. Particle, antiparticle. We have seen many YouTube videos. Then how can we call a particle and antiparticle as a pair? It's simple. For a particle and an antiparticle annihilation to occur, they should be of same flavor. Like up quark can only annihilate anti-up quark, down quark can only annihilate anti-down quark. If it's an up and anti-down quark pair, it can exist, but only for a short amount of time. All mesons are unstable. Like mesons generally decays into electrons and antiparticles and neutrinos. You can see here. Up and down, anti-down quark is pion, strange and anti-up quark is kaon, up and anti-down quark is again rho. You can see. Antimatter. How does it differ from matter? Antimatter has opposite charge. We all know that. Like electron is positive, while positron, which is the antimatter of electron, is positive. Electron is negative, it is positive. But do they have opposite spin? I will stop here for a while. Do they have opposite spin? Matter and antimatter, do they have opposite spin? Friends? Okay, I will carry on. Shall I carry on?
I think they do have opposite spins, no? Because we're antimatter, right?
Wait, I will tell. It's actually no, because for a matter and antimatter to have opposite spin, they must be entangled. Like let's say take an example of pair production, and when an very gamma ray photon strikes on the nucleus, electrons and positron is made. This is known as pair production. Since they are made at an instance, like they have a connection, they are entangled. Then matter, electron and positron will have opposite spin. If they are not entangled, they don't have to be spinning. They can spin in the same direction as well. It's simple. It's not simple actually. I didn't understand quite equations. Okay, let's get on to the topic. Antimatter have opposite color. Like imagine, you can't imagine actually, if mesons, take mesons. If one is red, the other should be opposite of the red color. There's no opposite of the red color. It should be opposite of the red color. When they combine, they have to be white. The electron and positron has to be, if one is red and the other has to be anti-red. We will see about this in quantum chromodynamics, and they also have to have opposite charge. We know that. And when matter and antimatter do annihilate, all energy of the rest mass is emitted. Like you can see, E is equal to mc square only here, because nuclear fission, fusion, everything, the energy is, all the rest mass energy is not emitted, but only during matter and antimatter annihilation, it is all the energy is emitted. Let's say about Higgs boson. It's a very fancy topic, because in news, every YouTube channel, they are talking about Higgs boson, and we will see about that. Higgs boson is Like other boson, is excitation in its field, especially the Higgs field. When a particle interacts with the Higgs field, it possesses mass. This is how all elementary particles have mass. It's not simple. When any fundamental particles interacts with Higgs field, it has mass. Higgs boson is the only elemental particle that has zero spin. You see here, you see Higgs boson at the last, it has zero spin, and it that's why it is called a scalar boson. Every fundamental particles has a spin and they are directional, but only the Higgs boson is not directional, and because it has zero spin. Higgs field can easily be understood by a popular analogy.
Now recording.
Higgs field can easily understood by using by a simple analogy of fish in water. Imagine you are a fish. You are surrounded by water. Then you don't know you are surrounded by water. It's like you have lived in your whole life. Then how you say then I'm surrounded by water? You are a fish in the water. You can't say that water surrounds you because you have lived in it for your whole life. So you don't know that water exists. Higgs field is exactly like that. You can't tell I can't see Higgs field. It's always around you. It gives you mass. So you can't say Higgs field is not around. A sharper fish is a lighter particle. A sharp fish like tuna fish with a very pointy nose can go inside the water in high speeds. But if you take example as a parrotfish or jellyfish, they are like very chubby and they can't go through very fastly because they interact much with the water. If you interact much more with Higgs field, you have higher mass. If you interact less, you have low mass. Okay, mass. The Let's take again for proton as an example. A proton has two up quarks and two down quarks. Up quarks and down quarks possess their mass due because they interact with Higgs field, right? The mass of the quarks only accounts for 1% of its total mass. Can you guess what is the 99% of the remaining masses? Hello? The mass of the quarks only accounts for 1% of the mass of the proton. Can you guess why? Should I have to repeat the question or should I continue?
No, you can go on.
Okay. We know that E is equal to mc square, right? But it can also mean m is equal to E by c square. Like mass is directly proportional to energy. The quarks are held together by a very strong force, which I said is 10 to the power 40 times stronger than gravity. The energy in their attraction is is accounting for the 99% of its mass. This also tells us not all of the mass are given by Higgs field. I will repeat, not all of the mass are due to Higgs field. Most of the mass in our observable universe exists due to the strong interaction between two quarks. Okay, that's it for my lecture, and Raguveer will continue on Large Hadron Collider.
Yeah, thank you, Ashwin. Okay, so now I'm going to talk about the Large Hadron Collider. Can everyone see my screen?
Yep, you can go on.
Okay, so this yellow ring that you see here, it is that is the LHC. So, but as you probably would have already guessed, this is not above the ground, but it is 100 kilometers under the ground. Can anyone guess why?
I think it's 100 feet.
Sorry, 100 feet. Okay, it's not underground because there might be a risk of radiation leak or anything like that. It's just that buying 27 kilometer of land in Swiss Geneva is very expensive. So before the LHC, there were many particle accelerator constructed in CERN, but we are only going to concern ourselves with the super proton synchrotron and the large electron positron collider. So the super proton synchrotron, it has a circumference of 7 kilometers, and it was able to accelerate the protons up to energy levels of 400 giga electron volt. This just means that the electrons are 400 times more massive than their mass, and I'll tell why in a bit. The Large Electron Positron Collider acted as a particle accelerator for electrons and the antimatter pair positrons, but they were only able to accelerate the electron up to 209 giga electron volt. This has to do with this has to do with something called synchrotron radiation. See, when you accelerate elementary particles in a circular motion, you have to maintain in order to maintain the circular motion, you use strong magnets. So when you use these magnets, something called as a synchrotron radiation leaks away from these particles. So in protons, the rate at which this radiation is emitted is much lower than the electron, and so it is much more easier to gain high speeds with accelerating proton than by accelerating with high energies by accelerating the proton than by accelerating the electron. The SPS the SPS was used to discover the W and Z bosons, which were predicted earlier in the 1970s. The Large Electron Positron Collider were used to measure the properties of W and Z bosons with high precision. This is because, as Ashwin told, protons are a messy bundle of two up quarks and a down quark. So they don't exactly collide in very precise ways. But the electron and positron are already elementary in nature, so their precisions are much more precise, much more precise. So this is just a picture for comparison. This is the superproton synchrotron. This is the LEPC, and the Large Hadron Collider was actually built in the same tunnel that was dug for the LEPC. But it was modified so that it is used to accelerate protons. Next slide. So I'm going to um, attempt to teach about the working of the LHC in 5 stages. So stage 1, we have the LINAC 2, which is a linear particle accelerator. Stage 2 is the booster, and it is a it's in the shape of a ring, because in the booster the proton reaches speeds of about 91.6% the speed of light, and doing this in a linear accelerator is very inefficient. The proton synchrotron and superproton synchrotron are basically the same as in the superproton synchrotron is much more larger than the proton synchrotron. And finally, we have the LHC. So this is how it looks. I mean, not exactly, but this is the basic layout of the LHC. So what the LHC does is it smashes the protons at 99.9% the speed of light. So this is achieved by 4 stages. Stage 1. In LINAC, the hydrogen atoms are stripped off of their electrons and they are accelerated to about 1/3 the speed of light. After that, they are divided into 4 and enter the 4 booster rings, where they are accelerated even further by using pulsating electric fields. Pulsating electric fields to about 91.6% the speed of light. The magnets keep their motion circular, and before entering the third stage, which is the proton synchrotron, they are combined into a single beam again. Here they are accelerated to 99.9% the speed of light. After this, the extra energy imbued represents itself as mass. So essentially, when the protons reach 26 giga electron volt, they are 26 times more massive than their rest mass. So after this, they are actually what happens is the LHC doesn't send a single beams of protons. So we know that proton beams need to collide. So 2 beams are sent at different time intervals. So 2 beams leave the proton synchrotron and enter the superproton synchrotron, where they are further accelerated to about 450 giga electron volt, which means they are 450 times more massive than their rest mass. Finally, they enter the LHC. The LHC has two vacuum tubes where both our beams rotate in opposite directions. Now, these tubes cross over at 4 places, but the beams aren't made to collide yet. They are imbued with furthermore energy from the pulsating electric wave and reach an energy level of 7 tera electron volt. That is, they are 7,000 times more massive. This also means that the magnets used to keep their motion circular need to be much more powerful. In fact, the electromagnets need to have 12,000 amps flowing through it. This is done by reducing the temperature of the magnet to 1.9 Kelvin, which is really close to absolute zero, making them superconductors. So after they've acquired enough energy, they are made to collide, and the resulting debris are detected and studied. So how do you find the Higgs boson? By smashing protons together. First of all, you need to understand a tiny bit of the concept of fields. As Ashwin said, the most fundamental parts of the fundamental building blocks of nature are fields and not particles. This is how we think of when we say particles. Particles are just fluctuations or ripples in the field, and these fields exist everywhere and have different values at different points in space, and these values can change with time. So, for example, the electron is a fluctuation in the electron field, and a quark is just a fluctuation in the quark field. So, likewise, the Higgs boson is a fluctuation in the Higgs field which gives mass to everything. So, imbuing enough energy to the Higgs field should create a ripple, that is, the Higgs boson. This is what the LHC did. When the protons collide, they create matter equivalent to 14 tera electron volts of energy. And the Higgs boson, we have a slight chance, if we are lucky, we have a slight chance that we may create a Higgs boson. But the next problem is the Higgs bosons only exist for 10 to the power of minus 24 seconds. So essentially, they don't even exist for long enough to reach the detectors. They are almost decayed instantaneously. So how did the scientists discover the Higgs boson? Well, the Higgs boson generally decays into two high energy photons, I should say. So this is what the scientists studied. The resulting protons. I'll show you a graph. The vertical axis here represents the number of pairs of photons emitted, and the horizontal axis represents the charge. As you can see in the lower graph here, at the energy range of around 125, the energy of the photons skyrocketed. I mean, not skyrocketed, but it was a little higher than all the other background photons. So this kind of high energy photon can only be emitted by a boson. So what's so special about the Higgs boson? Why is it such a big deal? Well, we saw in the standard model in Ashwin lecture that the Higgs boson is the Higgs boson itself isn't very important. The Higgs boson is important because it proved the existence of Higgs field, which gives the matter its mass. The problem was in 1960s there was a problem with the model, especially with the W and Z particles, which was if they existed they had to be massive. But when we gave them mass in the theory, the model broke down. We'll be seeing this in detail in the upcoming lectures in this series. I just told you this to give you a sort of an idea. So what's next for the Large Hadron Collider? So currently they are working on a high luminosity Large Hadron Collider, which means that right now it operates at about 400 million collisions per second. High luminosity Large Hadron Collider is just an upgrade so that the number of collisions per second is increased so that we can study the matter more distinctively. But the long-term plans are this. The next step of the Large Hadron Collider is to build something called as the Future Circular Collider, which would be about 80 to 100 kilometer in circumference. So what this says is that, actually, let me go back to a slide. So as you can see, the superproton synchrotron, the proton accelerators are used to reach high energy ranges. And the electron positron colliders are used to study the known ranges with high precision. So what we hope to do with this FCC and CEPC, which is the Circular Electron Positron Collider, is that the electron positron collider would be used to study the Higgs boson at much higher precisions, and the FCC would be used to discover new energy ranges and new types of matter. So, thank you. That's it.